Well, I suppose with the state of the network here, this is more of a fantasy kind of talk. But yeah, it's about IPv6. You're supposed to introduce yourself. So I'm Florian. I've been an OpenBSD developer for over 10 years. I've added a bunch of stuff and I deleted more stuff. So once the difference ever reaches 0, I will resign. And this year I made it up to 2,047 commits. And this is where this all started in 1999 with the KAME stack merged into OpenBSD. And the KAME project kept on. So this was a Japanese research project. This is all well before my time, and I'm not a historian, but so they eventually shut down in 2006, I think. Code got merged in from that project and also maintained in OpenBSD, but after that there was not a lot of actual development as far as I can see. It was mostly maintenance, making sure that the code still compiles, still works with changes in the network stack, that kind of thing. And well, to be honest, there was also not a great uptake of IPv6, of course. I would say that it changed in recent years. So we saw in the previous presentation how much IPv4 space costs, and people really can't afford anymore to run IPv4, I think. So we need to make sure that IPv6 gets better. I did a bit of work in IPv6. So this is a timeline, but we were more looking at it from a subsystem kind of perspective to make a coherent story out of this. And we're going to look at IPv6 on the edge, because like on your laptop, in your home network, that kind of thing, because in the core or on your server, it's kind of boring. It just works, and it has been working for a long time. It's just that nobody uses it. But you it works the same as IPv4. You configure a static address, you configure a default route, you spin up your server, you're done. It just works. But if nobody's using it, what's the point? And for people to use it, we need to improve things on the laptop, on users' machines, actually. And if you're looking at on your machine, you have IPv6 enabled, and you see maybe 4 addresses there. And the first one is a link local address that can be only used to talk to hosts on the same layer 2 network. The next one is a globally reachable address, which is formed out of a prefix and a key that's on your system. So it kind of looks random. And it is random from the outside, but it will stay the same when you stay on your network. Like you reboot your laptop, you request a new IP address, you will get that IP address. The next one is a temporary address, and that one is completely random. It is valid it stays around for a day, and then it will just disappear, and you get another random one. And we already have another random one, because IPv6 addresses can expire. They have a lifetime. They actually have 2 lifetimes. They have a preferred lifetime, the PL time, which is a 0 for the third address, which is then shown as deprecated, which means you can still use that address for existing communication, but you should not use it for new communication. And that's why we ended up with the 4th address, which is another temporary address which has a preferred lifetime that is bigger than 0. And you also have a valid lifetime. When an address reaches a valid lifetime of 0, it's invalid and it just disappears. This is like a DHCP lease expired in IPv4. Be quicker. So we have these 4 addresses, and we want to talk to a destination. How do we do that? We need to choose an address, and that is a source address selection. There's, of course, an RFC for this. And now, looking at the code in OpenBSD, there were comments that OpenBSD implements a previous RFC. And then, so the question was, do we actually need to do anything about this? So looking at the new RFC 6724, there are 8 reasonably straightforward rules in there what we need to do if we want to reach that destination. And these are those rules. So if your destination is on your machine, on your laptop, then just use it as a source. Source and destination is the same. Prefer appropriate scopes. So this was about the link local addresses. If you want to reach a link local address, you must use a link local address. You can't use a global address. They can't talk to each other. It does not work. Avoid the deprecated addresses. If you don't have anything else, well, you can still use it. OpenBSD does not implement mobile IPv6, so home addresses is not a thing. We don't care about that. Prefer the outgoing interface. So you can have multiple network interfaces, and before you do a source address selection, we're doing a route lookup. That's how we figure out that packet will go out there. Well, use an IP address that's on that interface. You can have unnumbered interfaces. Well, then use another IP, but prefer the one that's on that interface. We don't implement matching labels. It's maybe something I need to look into at some point, so we can ignore that. Then we prefer temporary addresses and use the longest matching prefix, which is a pretty weird one, which you will probably not run into your laptop. So, what the RFC is doing or imagining is you have a pool of IP addresses, which is your candidate set, and you boil this down to 1. So you have your candidate set of, say, you have 2 IP addresses left over, you want to reach the destination, then you just write them underneath each other, and you look, where is the prefix the longest? Well, it will probably not change on the addresses that you have on your laptop because they are all the same prefix, so the length is the same. It doesn't matter, but anyway. Now, if you're looking then at the code, you find this piece of code, and don't try to read the comment. And we are at rule 5 here. After that, we concern ourselves with temporary IPs and with the longest prefix thing. But this is not the code here. So that comes after this comment. So there's this comment which says, oh, yeah, this comes down to 2 cases. There's a lot of words, and then there are even more words. Roughly speaking, oh, this is going great. And then we have a table which lists these weird, like the second line is variables that are calculated in some strange way. And so we're saying the RFC imagined you have a candidate set and you boil this down to 1 IP address. What the actual code does to implement this is it picks 1 IP address. So you don't have any IP address. You pick the first one, and then it iterates over all configured IP addresses, and it compares them. Is the next one, is that better? Then swap them. This is what it asked about replace question mark. And sometimes you need to replace things, and sometimes not. So I'm staring at this table, and I'm staring at the code, and I'm actually doing this for days to figure out, will this ever reach a point where it needs to replace the current best IP address? And I come to the conclusion, no, it does not. There was no case where it would do anything. This is basically that code. And so my theory how this ended up is because of bit rot. So it claimed it implemented this RFC, but looking at the code, it did not have that much to do with the old RFC either. So I figure I know that they wrote the code and the RFCs kind of at the same time, and I suspect that this is some old stuff. And could not really figure this out from any CVS history or that kind of thing. And so eventually I decided, okay, let's just drip this all out and simplify this. And there were no regressions-ish. So it's supposed to do the same thing, and it kind of did. The problem is, you're supposed to arrive at a single IP address at the end, but the age rules don't provide this. You still need a tiebreaker at the end. And the old implementation picked the newest configured address, and the new implementation picked the oldest configured address, but just because of the way it was implemented. And this has consequences when with a flash renumbering event, which means that your ISP reboots and gives you new IP addresses, and you're using the old ones, but they are no longer routed. So they're still valid, but your ISP is no longer routing them. The ISP is not supposed to do this, but these things happen. Now, The reason in this change of behavior is because of the data structure that's used to store IP addresses on interfaces, and it is a tail queue. And so it would be easy to get back to the old implementation, basically always swap when things are the same. But that will break if someone ever wanders in and changes this data structure. Like if someone changes this into a simple list, we have the same problem again. So we want something that's independent of the data structure. And what I came up with is compare the lifetimes, which in practice works. You can construct cases where this does not work, but I think those are constructed cases. Now, there are actually 9 rules. And there's rule 5.5, which is preferred addresses in prefixes advertised by the next hop. And then it goes on and says, this is not applicable for if implementations do not track this. And basically, nobody tracks this. But this really got some traction in the OITF recently, where there's a lot of hemming and hawing. We really should do this. It's great. We need this. And people are writing drafts to make this into, you must track this and you must implement this implementation. Or it's probably you should. Not entirely sure. And so this is relevant for if you're multi-homing, like a small network, a small office, that kind of thing. If you're your own ISP and you have your own address space, it doesn't matter because you're speaking P2P to the outside and it just works. But if you have, if you're multi-homing your home office, you have 2 ISPs. They give you different addresses. You configure those addresses on your interface, and then you try to reach an outside destination. If you're routing out through ISP A, you must pick an IP address that ISP A gave you. If you use ISP B and route it out through ISP A, they will block this. So that's why you need to track where did this address actually come from. This used to work in IPv4 because everything is netted anyway. So your network uses RFC1980 addresses internally. It routes the packet somewhere to the router of the ISP or well, the CPE on your end. It nets and it goes out. So it does not matter there. Turns out this is pretty easy to implement. We're doing the route lookup anyway, so we have this information, except if you're trying to talk to localhost, there's no need for that, or multicast packets, but most of the time we do the route lookup where it matters. We do have space in the data structures to store the next hop. We can just abuse the space that we have for point-to-point interfaces where we need to store the destination, so we can just put the router in there. And we need to pass this up from userland, which is also easy because, well, we have point-to-point interfaces. We need to already be able to configure this. And the implementation looks like this. So this is, this function does the source address selection. We need to pass in the route structure. We need to check that we actually got one because, well, sometimes we don't have one for like localhost. And when it comes to rule 5.5, we could remove the comment, we do not track this information, because now we do. And then we check, is the IP address that we used actually from that router? And if not, then switch it. Yes?
Does it also work for point-to-multipoint tunnels like MGLE?
Unlikely. The question was, does it work for point-to-multiple-point tunnels? And I don't think so. I also don't see how you do SLAAC on there. So this is concerned with stated address auto-configuration. So I don't think so. Yes, but this is concerned with stated address auto-configuration. So what's going on about, well, you have these IP addresses on your interfaces. Where are they coming from? Well, a router gives them to you by sending an IPv6 multicast packet called a router advertisement, and this contains the following information. Hey, I'm a default router. You can use this /46 prefix, and I'm glad that PSLA is not here, to form your IP address and hope for the best that you don't collide with anything, which you probably won't because you have 2 to the power of 64 addresses in there, so that's fine. And hey, there are also some name servers that you can use. On the host side, your client, your laptop, what it then does is it waits for those router advertisements or it solicits them and uses the information to configure your system. The old way, as in KAME stuff, was split between kernel and userland. The kernel would listen for the router advertisement and then configure your system. It configures the addresses, configures the default route. And on userland, we had a thing called RT-sol, which sends out router solicitations. Now, this had some problems. The router advertisements are not necessarily particularly simple packets, and parsing them in the kernel has some security issues because you don't have any privilege separation or stuff like that in there, so that's not cool. And the kernel would just, so it parses them and forms an address and it would just jam this in. It was just put it onto the interface, which is awkward if you're trying to unlock the networking stuff in the kernel. So it's nicer to have this configured at one point where also all the other addresses come in. On the userland side, RT-sol, again, this old KAME stuff, from the early 2000s, it predates things like Wi-Fi or suspend resume. It imagines you run your desktop, you fire it up in the morning, it sends a router solicitation and waits for an advertisement. If none comes, it sends a router solicitation, waits, sends a router solicitation. If nothing comes, it just stops. So if you use it on a modern laptop and you wander to a new Wi-Fi network, it does not do anything. So you don't have IPv6 for 15 minutes because that's about the time when a new router advertisement comes by anyway. Or you suspend resume your laptop, it doesn't do anything. So the solution for that is rip this all out and move this all to userland. So I wrote slaacd for that. There's an entire presentation at the BSDCon in 2018, I think, about this. So it's privilege separated and it's pledged. So all the good stuff. It's always running. If you don't configure it, it doesn't do anything. And to configure it, you set the autoconf flag on your interface and then it starts to do work. It starts to send router solicitations. It keeps track of the state of your interfaces. Like if your Wi-Fi is roaming, you're moving to a new Wi-Fi network, it notices this, does new router solicitations. Same way for suspend resume, it notices the interface comes back up and it starts to do work. It figures out that on the new network that you showed up, there's actually no IPv6, so it starts to deconfigure the addresses to avoid breakage, which is also kind of important. And yeah, it handles DNS, multiple interfaces, multiple routing domains, all that stuff. So I was saying, there's this thing that sends you router advertisements, and the old and crafty way was router advertisement. And the configuration the man page for the configuration file had this nice tidbit. It obeys the famous termcap file format. Yes, so famous, infamous. I think it's kind of like a flammable and inflammable. They are both bad. So yeah, termcap, like it uses colons as separators, and yeah, that's great for IPv6. So I think what happened there is, like, it's the only parser that was available at the time, so let's just use this. So yeah, this thing needed to go. It was bad. So well, while we're at it and writing privilege separated network daemons, we might as well write another one. How hard can it be? Turns out not that hard. And while we're at it, we bring in a what we refer to as a parse.y based config file. So in parse.y, there's a YAC parser. It has its own lexer in there. And it's the standard way on configuring OpenBSD things. So if you, like HTTPD, PF, your window manager, CWM, uses this, if you use TWM. So if you configure something that does not, when you don't recognize this format, then you stepped into something ancient. All the stuff basically uses this. And what this does is we configure a bunch of name servers that get advertised. These are outside of the interface blocks, so the interface blocks inherit this, but you can also override this on an interface. And then we configure that we want to send router advertisements on two interfaces, VLAN 42 and VLAN 64. On VLAN 42, we say auto prefixes means, hey, look at on this interface to figure out what prefix is on there, and then use that to send the advertisements. But this is actually the default, so you can leave that out. And which is what VLAN 64 does. It leaves the auto prefix out, but it sends a NAT64 prefix, and we will talk about that at the end, what that does. You can also configure static addresses on here and give them lifetimes if you want to. But this is about the auto configuration, which we're talking about next. Because now the next question is, where do I get my prefixes from? So you're not your own ISP, you don't have your own address space, so you request the prefixes from your ISP. And you either request a single prefix or which is big enough to then split up into multiple prefixes for each interface, or you ask for multiple prefixes. And then we use that prefix information that we got from the ISP to configure the interfaces, and RAD picks that up. DHCP-CD from ports can do that, and I had some trouble understanding what the configuration actually means and how to use it, but I kind of got it to work. Now, this being OpenBSD, we of course want this in base. And wanting things in base always has this problem that needs solving. So you need someone who's sufficiently bored. You need someone who has a need to tackle that problem, and that person needs to be able to do something about it. It's always that. And in the past, we actually had, I'm aware of two diffs of where two people were sufficiently bored and they had the means to do something about it, but they didn't have a use. So those diffs went nowhere. They sent them to me and, yeah, cool, run with it, get it in. I'm happy to review it, but, well, they don't have a need for this. I did not have a need for this because, well, crappy ISP. And, well, then the stars aligned. And because suddenly we had someone who was sufficiently bored, who had a need, and could do something about it. Hi, that was me. Because my ISP rolled out DHCP-v6. So, cool, let's do something. Turns out the CPE they sent me was just too crappy to develop anything against it. You needed to request just the right thing. If you requested something wrong, it would stop speaking to you. And the only way to get it to speak to you again was a factory reset. Now, once I figured out what I actually needed to ask that thing, it would only answer once. Now, DHCP-v6 prefix delegations have a lifetime. You're supposed to renew them. The CPE would not answer. Like, I want to renew this prefix. I don't care. It would the ISP would still route the traffic to me, but yeah, it would not. So it would not answer to the DHCP request anymore. To only get it to answer again is, hey, factory reset. Now, the CPE was a critical piece of infrastructure, as in it drove my home office and that of my partner, and so I can't constantly factory reset. That's no way. So I kind of gave up on all this. I thought, I can't make this work. And I thought, and then I noticed something. Turns out I live in the EU. And we had a great keynote that talked about the EU. And one thing that applied to me is, that means I have to, I can bring my own device. My ISP must accept that I bring my own device. So I researched this, and it turns out other people also figured out that this ISP is particularly crappy and their CPE is shit, and hey, use this specific Fritzbox. So I put this up on the one page, and Misha and Ibsen jumped onto this within like an hour. Yeah, we get you that thing. And so I started to implement something. I transmogrified DHCP-LSD and developed this against Kia, which is ISC's DHCP server. I think it does all the things like V4, V6, all that good stuff. And yeah, so I had this running within like a day because it turns out DHCP v6 is not that different from V4. The state machine is slightly different. It has more features, but yeah, it's not that difficult. And so I was mentioning that I had some trouble figuring out what DHCP-CD's config is actually trying to do, and then reading the RFCs and looking what it actually does, it's a thin wrapper around, over the on-wire protocol, kinda-ish. So that was very weird, and so I thought, let's do better than this. And I was actually struggling a bit with this because you need to work out, hey, I want a prefix for these two networks. I need 2/64s for that, which is what this configuration does. I want 2/64s for one for VLAN 42, one for 62, but I need to request the covering one. Which in this case is easy. I request a /63. In the general case, this is actually quite difficult, and that is what DHCP-CD sidestepped. It said, well, you do the math yourself, and you tell me what you want. And I wanted to do the math in DHCP-6-LSD, and I kind of got this to work. I'm pretty sure there are some maybe weird cases, but well, I'll skip that. So to figure out what the thing is doing, you can run it in config check mode, and in verbose mode, it will spit back the configuration that you put in. Like, this is what I think you meant. This is what I'm going to do. And so what I then implemented is I put in some comments. So this is what DHCP-6-LSD is actually doing. It puts out the comments and it says, well, from what you told me, I figured I need a 64 for VLAN 42. I need a 64 for VLAN 64. And oh, by the way, you also want to reserve another 57. Cool. The splitting looks like that. And if I do the math to this, the covering prefix for that is a /56. So I suppose you also can now skip installing zipcalc from ports and just use DHCP-6-LSD to. Maybe not. Right, so we have that sorted. We have, like, to recap, we started with a laptop. We want IP addresses. We moved on to the router that needs to handle IP addresses, but the router also needs IP addresses, which gets it from the ISP all the way back to the laptop. So in the beginning, I was saying that IPv6 is kind of really picking up because it just gets too expensive to run v4, and not just because of the address space. It's also the amount of v4 you need in, so I have no idea, I did not look what they're doing here, but so you have a conference network, yes?
They have a huge network allocation, so they give public IPs out.
Right. But yeah, so if you don't have the public IPs, if you do private space, then oh, let's hand out a 24. How many people come here? I don't know. Yeah, 250. No, that's actually not enough because everybody brings a laptop and 2 phones and a tablet. Okay, so this is annoying. So you need that address space. You also need the capacity on your NAT that it can actually handle so many devices, which is all bloody annoying. And if your network is even bigger, it gets worse. So how about we try to do v6. And so this is a thing that also came out of the ITF, where Jan Linkova from Google was mostly driving this. The idea behind this is we want to. So step back. So there is a technology which browsers implement and your handheld devices implement. It's called happy eyeballs. What they're doing is, if you have v4 and v6 on your device, they do two connections to your web server or whatever. One over v4, one over v6. They let them race against each other. Whichever comes first back wins, and you're speaking that address family. So if you have misconfigured IPv6, you will never notice this because things will just work fine over v4. So if you then turn off IPv4 and you want to run a v6 only network, everything is broken. So that's annoying. So people don't do that. To get around this is, how about we let devices opt into this? And this is where the mostly comes in. So the network still provides IPv4 for the devices that can't do this, but a device that thinks, hey, I can do this, opts in via an DHCP-v4 option. It tells the network, hey, I don't need a lease. And the router hands back a pref64 option in the router advertisement. And that was the NAT64 prefix in the RAD configuration, which does this. Well, that's not what I thought. Where am I going with this? Oh, no, actually, I'm kind of done with this slide. So, now, you have that, oh, no, now I know what I wanted to mention about this. Many devices do this. Android, iPhone do this, macOS does this, Windows does this. So the only device that we're missing here, or the only OS that we're missing that runs on like laptops and that kind of things is OpenBSD, because I mean Linux on the desktop. So yeah, I totally wanted to implement that. So the way this works is you still need to be able to talk to IPv4 things sometimes. So for example, I had two examples. One is, I'm not going to mention that, and the other one is GitHub. So GitHub is v4 only. So if you have a v6 only network, you can't reach that. So that's annoying. The other thing is, there are things that use address literals or that fundamentally request an address family. So I can give an example for both, which is a ping. So you ping an IP address. So you ping quad 8, that's IPv4. There's no way around it. You can't magically upgrade this to IPv6. Well, turns out you can. By tunneling it out of your IPv6 only network to the edge, which can be, well, your router, or it can tunnel through your whole network. So if you're an ISP, you can run your whole ISP network with multiple hops IPv6 only, and only at the edge you do address translation. And this works because IPv6 addresses are quite big. There is a lot of space where you can fit the whole IPv4 internet in there. So you only need the /69 and 96. So this is a well-known prefix. So since the addresses are 128 bits and you need a 96 plus 32 is 128, so this fits perfectly. So what you're doing is you encode the IPv4 destination in the last 32 bits, send it on to a thing that runs the NAT64 translation. So it notices, oh, this is this well-known prefix. Let's drag the v4 addresses out again, do some network address translation, and send it on. On the return, it does the opposite. Now, That's on the server side, or that's what is referred to as the provider side translator. On the client side, the PF rule, so PF kind of can do this. The rule is massively more complicated. And there's a reason for that. So for starters, you need to set up the IPv6 address dynamically, because there's no way in PF to say, hey, pick the global address on that interface and put it in there as the from. That's not a thing. So if you're saying interface :0 for INET6, that's not what this gives you. It will give you link local address. So this is not going to work. Which means we need a daemon that sets this up. And I wrote another privileged separated network daemon because that's all I do. And I called it Gelatod as a nod to Michael Lucas, and who really likes gelato. And I claim if you squint just right, then gelato, SLAAC kind of sounds right. I really should not name things. Yes. So, and this whole thing is in ports because the configuration for this is massively convoluted, and Andrew gave a talk about how we don't like convoluted things. We want things just working, and this is the opposite of just working. And the reason for this complication is that AF2 only works on incoming rules. But on the client, when you send a packet out, you need a pass out rule because you don't see the packet going into the network stack. It only goes out of the interface. So what this configuration does is it sets up two pair interfaces, puts one into a different routing domain. The traffic enters a pair 1 because that's where the default route, IPv4 default routes to points through there to the other end. It then enters our domain 1 where it is an incoming. So this packet is coming in on pair 2. And then we can do all the rewrite magic and punt it back to our domain 0 and send it out. This is, I don't know, Todd Freeze kind of crazy, but it works. So yeah, this kind of needs improving. And what I looked into is, can I remove the pass-in limitation from AF2? And so I looked at the code and where this came from, and I think the limitation comes from because this AF2 is a transmogrified route 2. Where this is actually true. So the comment says this only works on incoming rules because we are doing a route lookup. So we already did the route lookup, so we can't do it on a pass out rule because we can't change the routing table, the routing information anymore. This is not actually true for AF2. I hacked around in this and I got ICMP working-ish. It's a bit weird, and UDP definitely works. TCP is horribly broken, and the server side is also now broken. So that's not cool. The thing is that on the client side, we technically don't need stateful rewriting. The RFC actually says that this is a stateless rewriting. So, I mean, in OpenBSD we kind of don't care because we run PF anyway, and it does stateful, so we might as well do that. But maybe it's easier to not do this in PF, but do it the macOS way, where they have an extra IP address on the interface, the last IP address. And they configure the NAT64 prefix. It's kind of a typo here, but anyway. And then they do this just stateless. I'm looking forward to Alexander Bloom's talk tomorrow, who will explain to me how a packet traverses the network stack so that I can actually implement this and can figure this out. I think I need IP input for this, maybe. But yeah, that's all I have for you. And we have 5 minutes for questions. Yes, please.
Do you actually need the address on pair 1, or could you use an interface next hop route instead of an indirect IP-based next hop?
I did not fully catch that. Can you?
The Gelatod configuration example, do you need actually the .1 address, or could you just use an interface address as the interface route as your default layer?
I think you need it. Sorry?
Wouldn't it be enough to set eFace or EFA?
Yes, but then that's.
You need the source address, of course, but do you need the destination address?
I think you need it for the routing table, but not 100% sure.
Okay, quick question. Just the old stateless auto config, you were saying that you play the kind of the lotto, that you don't collide with someone else.
Yes.
Is there any reason why you don't do, let's say, the IPv6 equivalent of an ARP, like, is there anyone host using this?
Oh, yes, of course, sorry. Also, I realized I should repeat the question for the stream, I guess. The question was, do I actually have an example for this? No, I don't have this in my slides, do I?
Well, you made the comment just.
Yeah, I just made the comment. I can go to slide 2 where it was slide 4. So the question was, so I made the comment that you get handed a /64 and form an IP address out of that and hope for the best. And then the question was, why don't you just probe if that IP address is already used? Like send an ARP request. In IPv6, this would be a neighbor discovery. Yes, and that's actually what happens. There's a thing called duplicate address detection, which does exactly that. So you chose an address, you configure it on the interface, and then the kernel sends out a neighbor solicitation. Hey, I want to talk to this IP address that I'm about to configure. Is anybody out there? And if nothing comes back, then that IP address gets chosen. And slaacd notices this if this happens, that the IP address does not get configured. And so I was talking about that this IP address looks random, but it's static. What actually happens is if a collision is detected, there is a counter in there, and that counter gets incremented by 1. So your IP address is not counted up 1, but this IP address is formed out of a hash. So you put in a prefix, you put in a key, and a counter. The counter starts at 0. Hashes this is the IP address. If there's a collision, increase the counter to 1, hash it again. It's completely random somewhere else. So your chances increase that there's no collision. This is attackable by always answering, yes, that's my IP address. So if No, I think so. The question is, you don't, because I think because I made that comment, this is attackable by always saying, hey, that's me. You see, the comment was, so you don't want to do this on the router. No, I think the correct answer to that is you must trust your layer 2 network. If you can't trust your layer network, then you have lost. There are too many attacks against IPv6 if you can mess around with a layer 2 network. And it's the same with IPv4. Like, it gets really difficult.
Those DHCP servers also sometimes test if the IP is taken, even though it, so you could just respond or on V4 and sort of empty the user state.
Yeah. Yes, Paul.
First off, I wanted to thank you for DHCP 6 release. We very much appreciate that. Thanks. But I wanted to ask, you mentioned temporary addresses for ongoing connections.
Yes.
That breaks long-living connections.
Yes.
So if you use SSH from your machine and you use IPv6, have your machine running for a day, suddenly your connection stops working.
Yes, type faster. No.
No. If you are using the connection, it still breaks because the address becomes invalid.
No, my joke was about, oh, you're logging into a machine and configure it. Well, don't take longer than a day to configure your machine. No, but no, you chose your source IP address. Like SSH, I think it's -B, I think, maybe. So you can tell it to use this source IP.
For SSH, this is a solved thing indeed, but
Yeah.
for other long-lived connections,
Yeah.
it might be.
You also wanted to jump in, Max?
Actually, on Mac OS, it keeps the connection open. Well, it keeps the address in temporary.
If it's in use
If
by
it's in use by any session.
Oh, yeah.
You will get actually a new one that is still temporary, and the other one will become deprecated, but you still have it. It won't be used for new outgoing connections, but the ones you have already established, they're kept and it works.
Yes, but that's how preferred lifetime works. I had interpreted this as the valid lifetime.
Yes, so the valid lifetime expires. On OpenBSD, the connection just stops.
But on Mac OS, the behavior is different. It just keeps it on. So in the office, you're at the NCC, you have V6, you will notice you get a bunch of addresses by the end of the day.
This is actually something that I want to test because, I need to repeat this. So the argument was if the VL time goes to 0, then on OpenBSD your connection will drop because that address gets deconfigured, and on macOS that address is still being used because you have an you use that address. That seems like a violation of an RC. Like you're kind of not supposed to do that. But when, looks like something I want to look at, yes. Yes?
Is there any plans to write or to port IPv6 to the OpenBSD instead of having people using the HTTP-CD instead? Because every time someone does a DHCP for IPv6, you have to pull in the HTTP-CD from the port tree.
I'm not entirely sure if I catch this. Was this about DHCP server that hands your IP addresses?
Yes, it's about, so there's two DHCP servers.
Yes.
You've got DHCP, which is OpenBSDs, and you've got DHCP-CD, which is from the port tree. Is there any plans to have IPv6 support in DHCP-D so that you can use a single daemon instead of using both?
Not currently because of the 3 problems, as in, yes, I'm capable, but I don't have a need. And it would not end up in DHCP-D because that's too old and crafty, and no, this would be a new writing. But it's probably not massively complicated. I think I'm getting kicked out here.
So, let's thank our speaker, and this is a small token of appreciation from the
Thank you.